identifying quadratic functions. We'll look at the graphs, the equations, tables, and contexts of quadratic functions. Let's start with the graphs. Here are 3 graphs of quadratic functions and 3 more graphs. Do you notice anything that is similar about these curves? A quadratic function, the graph will be in the shape of a parabola. It's a U-shaped curve, which will either open up or down. And there'll be a high point or a low point called the vertex. It's the turning point where the graph changes direction. Graphs that are not quadratic functions, so we'll call these non-examples. The first one here is linear. Then we have an absolute value function. This next one is not a function at all because it does not pass the vertical line test. Bottom left is called a cubic, and the bottom right, although it might look like a parabola, it's too flat on the bottom, so this is actually a 6th degree equation. So now we'll look at the equation form of these graphs. This linear function, the equation form will be y equals mx plus b. The absolute value function will have these absolute value bars. This graph on the right that's not a function, the equation form is x equals y squared plus 2. The cubic function is y equals x plus 4 quantity to the 3rd power. That's why it's called a cubic. And the 6th degree function is going to be raised to the 6th power. So y equals, in this case, 1/3 x to the 6th power. Now let's take a closer look at the equations of quadratic functions. The top left is called the parent function. It's the most basic, it's the most general, it's the one we want you to recognize, y equals x squared. The next one is just shifted down 6, so it's y equals x squared minus 6. The next one, notice, opens down, so there'll be a negative sign out in front. On the bottom row, the far left, it's quite narrow, so both sides of this are steeper than the parent function. So we're going to, in this case, be multiplying by 3. The next one is quite wide, so we'll be multiplying by a fraction. And the one on the far right opens down, and it's been shifted 5 to the right. So what do you notice about every single equation of a quadratic function? I hope that you're noticing that every equation will have a y term and an x squared term. And if the x has something with it, in parentheses, that's just indicating a left or right shift. Now let's look at the tables of non-examples. So in this linear table, notice as x is increasing by 1, let's figure out what our y values are. And as x increases by 1, y is increasing by 2. This particular graph has a positive slope, so therefore we expected y to be increasing as x increases. In a linear function, there'll be a constant rate of change. It will always increase or always decrease and at the same rate. Now this cubic function on the right, I can see that it's always increasing, but not at a constant rate. So let's look at our y values as x increases by 1. 8, 27, 64. These y values are jumping up in size rather quickly. So in a cubic function, like the one that we're looking at here, the rate of change in this case will always be increasing, but at a non-constant rate. Sometimes you'll have a cubic function that'll be always decreasing, again at a non-constant rate. What we're interested in is, instead of a graph of a quadratic function, if I gave you a table of values, can we spot from the table of values that this is indeed quadratic? Well, first of all, let's write down our corresponding y values to each x value. Now, as x increases by 1, what's happening to y? Well, to go from 9 to 4, I'm subtracting 5. To go from 4 to 1, I'm subtracting 3. Then I'm subtracting 1. But at the vertex, it changes directions. To go from 0 to 1, I'm adding 1. Here I'm adding 3, and then to go from 4 to 9, I'm adding 5. So my first rate of change is not constant. I didn't expect it to be constant because the curve is at first decreasing, and then at the vertex it changes direction and it's increasing. Let's look at the second difference. How do I go from -5 to -3? I'm adding 2. How do I go from -3 to -1? Again, add 2, add 2. To go from 1 to 3, I add 2, and to go from 3 to 5, I add 2. So it's interesting that the second difference of this quadratic function is constant. Let's look at a quadratic function that opens down. And let's write down our y values for each x value noted in the table. I'm just grabbing these y values right off of the graph. How did I get from -9 to -4? I'm adding 5. How do I go from -4 to -1? I'm adding 3. Then I'm adding 1. To go from 0 to -1, I subtract 1. Then I subtract 3, and I subtract 5. So in the first difference, we don't have a constant rate of change. Let's look at the second difference. To go from 5 to 3, I subtract 2. And then subtract 2, subtract 2, subtract 2, and subtract 2. So I'm noticing that in the table of a quadratic function, if I don't have the graph, I don't have the equation, but I am given the table, I know that the second difference will be constant. All right, finally, what kind of word problems or contextual situations would arise from quadratic functions? Let's consider a bridge that may be familiar to you. This is the Bourne Bridge. If you go over this bridge, you get to Falmouth, that end of the Cape. The bridge in the far distance is the Sagamore Bridge, which gets you to Hyannis. Notice I could lay this bridge over a coordinate plane and find 3 or more points that lie on the graph. Turns out these 3 points would form, there is a unique function that would go through, a unique quadratic function that would go through these points. So let's just say that for context, definitely bridges are a familiar context for quadratic functions. Also, anything involving maximizing, whether area or profit. Motion problems, the motion of a projectile or a hockey puck as it travels in the air toward the net. The path of a thrown football. These are all examples of quadratic functions.